Welcome back on my YouTube channel. Welcome back on my physics corner. Today I'm going to share you about how to solve this question. Actually, this is physics paper 2 AS level structure question 9702 slash 2. This is on my June 2020. So don't go anywhere, and please, before you're watching my video, don't forget to subscribe. Don't forget to subscribe. Okay, let me check about question 1, 2, and so on and so on. I scroll up. This is data, and this is formula, and blank page, and this one number 1. So let's check about question 1. Define velocity. Oh, actually I already type here. This is on the right side. You see this. This velocity is change. Change. This is change in displacement. Per unit time. Okay, that's it. Or sometimes we use is as the velocity is delta x over delta t. X as the displacement. This is displacement, and delta t is unit time. Time. Sometimes this is in meter and this is in second, so meter per second. That's it. Okay, we go to question B, number 1B. The drag force Fd acting on the car moving with speed v along straight horizontal road is given by Fd equals to v square ak, where k is constant and a is cross-sectional area of the car. Determine SI base unit of k. Okay, we find both k units of k. Start from the equation that Fd equals to v square a times k. When we go directly into unit, unit force in Newton, or same thing with kilogram meter second minus 2. Then velocity is meter second minus 1, and they have square. And then A is cross-sectional area. The unit is meter square times k. So maybe we open first about equation this one, meter square second minus 2, and meter square also times k. So maybe we can cancel one about meter. Meter, and also second 2 is, we can cancel it. So k, we can get k as kilogram, and then meter is power minus 3. Minus 3. This one. Minus 3. Okay, that's it. Done. Okay, this is the unit of k, kilogram meter minus 3. Okay, continue to see question. The value of k in SI base unit for the car in B is 0.24. The cross-sectional area A of the car is 5.1 meter square. The car is traveling with constant speed along a straight road, and the output power of the engine 4.8 times 10 to the power 4. Yeah. Assume that output power engine is equal to rate which the drag force Fd is going to work against the car. Yeah. Determine the speed of the car. So I think actually we only use this formula. Yeah, use this formula and define about V. But we need to change in terms of power. Yeah, and we have constant 0.24 and A is 5.1. Yeah, so FD, yeah, same thing with power is force times V. Yeah? So force equals to P divided V. So from this equation, FD we change P per V, yeah, equals to V square A K. Yeah. So K we change, yeah, K we change V this at V square, yeah, equals to P V this is power 3, yeah. V power 3, yeah, V power 3 equals to P divided A times K. So power is 4.8, yeah, times 10 to the power 4 divided A is 5.1 times 0.24. Okay, I use the calculator here for find this equation. Wait. Four 4.8 divided 5.1 divided 0.24. These are about 39.21. Yeah, 3.91. Yeah. Times 10 to the power 4, or yeah, root of 39. Yeah, 39 point. This is something like root 3, yeah, of 3.91 times 10 to the power 4. Yeah, this is maybe about 3.39. This is about 3.39. Yeah, this is about 3.39 or 3.4. Yeah. Meter second minus 1. That's it. This one, yeah. Okay, I hope you understand about this, and we go to the next number. Question 2. Figure 2.1 show the velocity time graph for an object moving in the straight line. Okay, determine an expression in term u, v, and t for the area under the graph. Okay, for the area under graph, I think this one, yeah, shaded area is about trapezium. Yeah, Same thing with like u plus b divided 2 times t. Yeah, this one. This is actually trapezium. Yeah, trapezium area. Trapezium area, or actually same thing with like u plus t plus half a t square. Yeah, same thing with this one. Yeah. Okay, that's it. State the name of the quantity represented by the area under graph. Oh, this displacement. Yeah, this is displacement. This is displacement. Yeah. Displacement. Oh. Okay, we go to the next number. Yeah. Sorry. B question. A ball is kicked with velocity of 15 meter second minus 1 at the angle 60 degree to the horizontal ground. The ball then strikes a vertical wall at the instant when the path of the ball becomes horizontal. Okay. As the shown, figure 2.2. Yeah. Assume that air resistance is negligible. Okay. By considering the vertical motion of the ball, calculate the time it takes to reach the ball. Okay, we will use the formula about V equals to U plus GT, yeah, or maybe this is not plus, yeah, minus, negative. Why negative? Because they have moved upward, yeah, like they have gravitational deceleration, yeah. So on the maximum point, yeah, become horizontal. So this is u equals to 0, yeah. So 0 equals to u is 15 meter second, and g, let's say g we use 9.81, yeah, t, yeah. So t equals to 15 divided 9.81, yeah, about 1.5 actually. 15 divided 9.81, it's about 1.52, 1.53 second. That's it. Okay, this the answer is. Then continue to the next number. Oh, what is this? Explained by a horizontal component of velocity of the ball remains constant as it moves to the wall. Oh, because there is no force acting on the they doesn't have any force here. Total force here, horizontal direction is 0, yeah, or yeah, because they don't have any force, the acceleration is 0, yeah, the acceleration is 0, yeah. So since the acceleration is 0, the velocity is constant, yeah. That's it. Okay, we back to the next question. On the question I. Yeah. So that the ball streak with the wall horizontal velocity is 7.5. Oh, okay. We only use the Vx here. Vx. V on the direction x is u times cos. Oh, sorry. Oh my god. Cos the angle is 60. Yeah, cos 60. So oh wait. So the well, horizontal velocity. Yes, correct. Yeah, u is 15 and then cos 60 is half. So same thing with 7.5. Yeah, meter second minus 1. Yeah, that's it. Done. Okay, two more numbers, actually one number C, but they have two question, but I and I. Yeah, let me solve about C question. The mass ball in B is 0.40 kilogram. Its contact with the wall in time 0.12 0.12 second and rebounds horizontal with speed 4.3 meter second minus 1. Use this information from BII to calculate the change momentum on the ball due to collision. Okay, let's say this is a wall. Yeah, they have velocity ball in initially on the right direction is 7.5. Yeah, 7.5. They have 7.5 in initial. Yeah, 7.5 meter second minus 1, and then rebounds. Yeah, at the 4.3. Yeah, meter second minus 1. So change is in momentum. Yeah, delta P. You can say this is mass V minus V after rebounds. Yeah, so they have mass 0.40. Yeah, and velocity, the second velocity is 4.3. Then this is minus. Yeah, so when we see on the ball rebounds is positive. Yeah, so this is something with negative. Yeah, 0.40 times 4.3, this is plus. Yeah, because minus. Yeah, so maybe when I repeat again about delta P. Yeah, here. Yeah. Delta P is mass 0.40. Yeah, they have 4.3 minus 7.5 in minus. Yeah, so plus. Yeah, this is same thing with 0.4, 4.3 plus 7.5. So 0.4 times 11.8. Yeah, 0.4 times 11.8 equals to 4.72. Yeah, this is 4.72 in kilogram meter second minus 1. Yeah, that's it. Okay, this is the answer. Yeah, and we have one more question on the question II. Yeah, calculate the magnitude of the average force exerted on the ball by the wall. Oh my god, average force exerted on the ball by the ball. This is something with change momentum. Yeah, I go to here. Here, yeah. Force, yeah, equals to delta P over delta T. Yeah, we have delta T is 472 and delta T is we have 0.12 seconds. So we divide 4.72 with the 0.12 equals to 39.3. Yes, this is about 39 Newton. Okay, that's it. Okay, I hope you understand. And please, if you don't mind, please press the subscribe. Subscribe this channel. We go to the next number. Question 3. Explain what is meant by work done. Okay, work done is actually when we have let's say we have one block, and we drag it with force, and they can move until this something position like this one. This is D. So work done is force times D. So we can say in here, work done is force times displacement. That's it. Force time displacement. Then question B, a ball of mass 0.42 kilogram is dropped from the top of building. The ball falls from the rest stroke a vertical distance 78 meter to the ground. Air resistance is significant so that the ball reaches constant or terminal velocity before hitting the ground. The ball hits the ground with a speed of 23 meter second minus 1. Calculate for the ball falling from the top of the building to the ground. The decrease in gravitational potential energy. Okay, and increase the kinetic energy. Okay, potential energy, as you know, this is equals to mgh. So we have mass 0.42 and we have gravitational acceleration 9.81 and h 78. So this is equals to with this is about 321. 321 joules. That's it. Here 321 joules. Okay, the second one on the BI, the increase in kinetic energy. Kinetic energy, they ask me, the ball falls from rest. From rest, it means they don't have any velocity until they have velocity on the terminal velocity 23 meter second minus 1. So we can decide as kinetic energy, Ke or delta, this is something also delta, is about a half m v square minus u square, yeah. So a half mass is 0.42, yeah, then v is 23 square minus 0 square, yeah. So we get 23 square, yeah, times 0.21, yeah. Oh, this is about 111, yeah, this is 111 joules, yeah, that's it. So go to the question I still on the question B, yeah. They asked me about use the answer BI, yeah, to determine the average resistive force acting on the ball as it falls from the top to the building from the ground. Okay, actually we have work done, yeah, work done by resisting force. Work done by resisting force is we have they wants about force, yeah. Oh yeah, same thing with force time distance, yeah. Work done like change without between potential energy and kinetic energy change, yeah, between 321 and 111, yeah. This is equals to F, and they have D as the age, yeah, height, yeah, about 78 meter, yeah, about 78 meter before hitting the ground, 78, yeah. So I calculate this, yeah. Force equals to 321 minus and divided with 78. Oh, this is about 2.69, yeah, or maybe we round off, this is about 2.7 Newton, yeah, that's it. Okay, that's it, yeah. Okay, I hope you understand, and please subscribe, yeah, don't forget to subscribe. And we go to the next number. Oh, about grab. I think the last number on this number, the last question on this number. The ball in B is dropped at the time t and hits the ground at time t equals to t capital, yeah. The acceleration of free fall is g, yeah. Okay. On the figure 3.1, sketch a line to show the variation of acceleration. Acceleration A of the ball with time t from t equals to 0 until t equals to t capital, yeah. Okay, the graph, because they have constant speed, constant velocity or terminal velocity, something on the t, yeah, t something, they have like zero, yeah, zero acceleration. This is zero acceleration. And from g, yeah, until t something, they have like decreases in gravitational, decreases in acceleration. So like they have like yeah, okay, until the terminal velocity, yeah. This is decreases, yeah, and then this is terminal velocity, yeah. Then the acceleration becomes zero, yeah, constant speed. And from the g until sorry, mm, uh, I do for here, yeah, I do here, yeah. This is like here and here. This is until t, this is until the terminal velocity, and here is g, and this is graphic acceleration in meter second minus 2, yeah, and here t in second. That's it, yeah. Okay, thank you. I hope you understand. If you have any question or something else to chat with me, please text on the columns box, yeah. Thank you. We go to the next number, yeah. Question 4a. State the difference between progressive wave and stationary wave in terms of the transfer of energy along with, yeah. About transfer of energy, this is the differences between the progressive wave is transfer of energy, the energy transferred by progressive wave, but in stationary wave it's not transfer the energy, yeah. So we can decide here, yeah, the progressive wave, yeah, this is transfer the energy, yeah. Progressive wave, yeah, is transfer the energy, but stationary wave, yeah, is not, yeah, transfer the energy, yeah, the energy. That's it, yeah. The differences between progressive and stationary wave about transfer the energy or not, yeah. Okay, now question B is a progressive wave travel from left to the right along stretch string, figure 4.1. So part of the string at one instant. Okay, we have P, Q, R, yeah, are three difference point along the string. The distance between P and R is 0.48 meter. The wave has period 0.020 second. I use figure 4.1 to determine the wavelength of the wave. Oh, wavelength, yeah, okay. This R, yeah, actually from this point until R, this is one wavelength, yeah, one wavelength. So from this point until P, yeah, this is a half, yeah, a half wavelength. So 0.81, sorry, 0.48, yeah, meter. This is something what 1/2 lambda, yeah. So lambda is equal 0.48 divided 1.5. This is about 0.32 meter. This is lambda, yeah. Then the second one, calculate the speed of wave. Okay, the speed of wave v equals to lambda over t, yeah, or sometimes lambda times f, yeah. But because we already have a period 0.020, yeah, so we use lambda over period, yeah. Okay, lambda is 0.32 divided 0.002, yeah. Yeah, this is about 16, yeah, 16 meter second minus 1, yeah. Okay, that's it. 16 meter second minus 1. That's it. Okay, then question B. Let me check. Still in this. Oh, determine phase difference between Q and R. Q and R, yeah. Q and R is this phase, yeah. They have like 1.5 lambda, yeah. This is something with 1.5 lambda, or yeah, we can decide this is the same thing also with a half lambda, yeah. Why? Because we don't use about multiplication 1 2 3 and so on, yeah. So also lambda, this is something with 360 degree, like one circle, yeah. So we can decide phase difference, yeah. The phase difference, yeah, is 0.5 of lambda is 1/2 of lambda. That's the lambda, same thing with one circle, or 360 degree, and also same thing also with 540, yeah. This is like 360 plus 180, that's it, 180, yeah. Okay, that's it, yeah. Okay, now continue to the next question. Yeah, still in this question, maybe, yes, correct, still in this question IV. Figure 4.1, so the position string times 0, yeah. Describe how the displacement of point Q on the string varies time from T0 to 0.10. Okay, here from T0 until T 0.0. So you said this, the period is 0.02, yeah. So when they ask me about 0.01, it's mean like a half of period, yeah. This is like a half period, yeah. So we can decide, describe how the displacement from key on the string varies from the key. We see this from the key, yeah, here. So a half, yeah, here, yeah. This is something with a half of lambda, yeah, that we have lambda is 0.32. So from K, yeah, displacement, yeah, yeah, maybe with K is on, okay, here, yeah, okay, sorry. So this is K, yeah, Q, sorry, Q, and they have like and the period is 0.02. Second, yeah. So until this point, yeah, same thing with a half lambda, yeah, or a half lambda is the displacement is 0, yeah, the displacement is 0. Sorry, is 0, yeah, or 0 amplitude, yeah, when the maximum amplitude is in here. This is like a fourth of lambda, yeah, and also 3/4 of lambda. Yeah, that's okay. I hope you understand about what I explained. So we try to continue C equation, yeah, on this equation. Yes, a stationary wave is formed on a different string that is stretched between two fixed points x and y. Okay, figure 4.2 shows the position of the string when each point is at its maximum displacement. Explain what means by node of a stationary. Node is zero displacement. Yeah, node is zero displacement. Node is zero displacement. Yeah. Sorry. Zero displacement. Yeah. Why? Because they have on this position, yeah. This is node, yeah, node. This is also node, yeah. This is node also, yeah. In the position x, this point and this point, yeah. The y also node. Okay, state the number antinode of wave to shown in figure 4.2. We have two, yeah, we have two. So I repeat again when we have, yeah, we have like this one, right? This is equilibrium. So this is node, this is node, and this is node, yeah, on this point, and this point, and here is antinode, this point, and also this is antinode. So we have two, yeah, we have two antinode. Then state the phase difference between W and Z. W and Z is here, yeah, I think here, this is Z, this is W. So like how much wavelength is this one? This is 4, wait, this is like 1/4 plus 1/8. Yeah, this one is 1/4 here, yeah, and 1/8 is in here, yeah, of wavelength, of phase, of 2 pi, or in times in 360 degree, yeah. So this is like something with 3/8. Am I correct? 3/8 of 360. So equals to how much is it? 360 times 3 divided 360 times 3, 270 degree, yeah. That's it. So here is 270 degree. That's it. One more question. A new stationary wave is now formed on the string. That new wave has frequency that is half of the frequency of the wave shown figure 4.2. The speed of the wave is unchanged. On figure 4.3, draw the position of the string for the new wave when its point its maximum displacement. When its point is at its maximum displacement. Okay, because they have new frequency, the frequency is a half. Yeah, half of frequency. It means total wavelength is like a half. Yeah, you see this is a half. So the graph is only 2 node and 1 antinode, like this one. Yeah, like this one. Yeah, like the one. They have 2 node and 1 antinode. That's it. Because frequency a half. Yeah, frequency a half. So like a half wavelength also. Yeah. Okay, that's it. Okay, I hope you understand about what I explained it, and please don't forget to subscribe. Help me to subscribe this channel. Then continue to number 5. Yeah. And if this question, this explanation, or this exam style is can help you, you may to share to the others. Yeah. Okay, question 5. One of wire is attached to a fixed point. Force F is applied to the wire to cause extension X. The variation of with F of X is figure 5.1. Okay, we have on the X direction is force, and then on the vertical direction X is extension. Yeah, Y direction is X or extension. Figure 5.1, the wire has a cross-sectional area of 4.1 times 10 to the power -7. Yeah, and is made for metal. Young modulus is 1.7 times 10 to the power 11. Assume that cross-sectional area of the wire remains constant as well as the wire extends. State the name of law that describe the relationship between Fx. So in figure 5.1, this is about Hooke's law. Yeah, this is about Hooke's law. Hooke's law, that force equals to K times delta X, or maybe this is only X, because we see this on the diagram only put X object. Yeah. Okay, Hooke's law. Then we have other question. The wire has extents of 0.48. Okay, this is 0.48 of extents. Yeah, determine the stress. Stress is force over area. Yeah, some stress is force over area. Force is, we see this when 0.48 millimeter, they have force is in here. 48 is we zoom in here. This is 48. Here 48. So force is here 36 Newton. Okay, we back again. We zoom out here. So force is 36 Newton. Yeah. Divided area. Area is still same. minus 7. So okay, we calculate this. Yeah, 36 divided 4.1, it's about 8.78 or 8.8. This is about 8.8 times 10 to the power 7 Newton meter minus 1. Yeah, okay, we have this as the stress, and strain is extension divided initial length. Yeah. Oh, I think we don't use this formula, but we use modulus Young. Modulus Young is stress per strain. Yeah. So when they ask me about strain, yeah, strain means stress. So modulus Young is here. Young modulus is 1.7 times 10 to the power 11. So strain equals to 8.8 divided 1.7. Yeah, it's about 5.2 times 10 to the power negative 11 minus negative 4. Okay, without unit. Yeah, that's it. Here strain is 5.2 times 10 to the power negative 4. Okay, done. Yeah, we use this formula. Yeah, modulus Young equals stress over strain. So strain equals to stress divided modulus Young. Yeah, modulus Young, we the symbol is E capital. Yeah. Okay, we continue C question. Yeah, we have still 2 questions in C and D. The resistivity of metal wire 3.7 times 10 to the power negative 7. This is rho. Yeah, resistivity. Determine the change in resistance of the wire when the extension X of wire changes from X 0.48 to X 0.60. Okay. Let me check by the equation, by the formula. Yeah. R means rho L over A. Oh, I see. So when they ask me about delta R, this is same thing with rho delta L per A. Yeah. Okay. Go here. Delta R equals to rho is 3.7 times 10 to the power negative 7. Yeah. And then delta L is, yeah, this is 0.60 minus 0.48, but this is in millimeter, so we need to convert into meter, times 10 to the power negative 3. Yeah. Then divided A cross sectional area is we have 4.1. Yeah, this is 4.1 times 10 to the power negative 7. Okay, so maybe we can cancel first about 10 times 10 to the power 7 first. Yeah, here and here. 1.08, yeah, times 10 to the power negative 4. ohms. Yeah, that's it here. Okay, then a force greater than 45 Newton is now applied to the wire. Yeah, describe how it may take it that the elastic limit of wire has not been exceeded. Oh, when they have back again, yeah, to original length. Yeah, we can say this is when the wire can back into, yeah, original length. So we can say this like elastic limit. Yeah, check to the elastic limit or until wire is broke. Yeah, okay, that's it. Yeah, I hope you can understand what I explained here. Yeah. So we can continue to the next number. Yeah, the next number is number 6 about electricity. Here, question 6. A battery of electromotive force EMS 7.8 volt and internal energy R is connected to a filament lamp as shown in figure 6.1. Yeah, okay. Figure 6.1 is we have EMF 7.8 volt and external resistance, it's about lamp, and internal resistance is R small. Yeah, at a total charge of 750 of charge. Yeah, move throughout the battery, time interval 1500 second. During this time filament energy 5.7 kilojoule energy. The EMF battery remains constant. Explain the term in terms of energy without calculation. Why the potential difference across the lamp must be less the EMF of the battery. Yeah, so because they already absorbed by internal resistance. Yeah, so like internal resistance less than resistance. Yeah, less than internal resistor. Yeah, less than resistance then lamp. Yeah, internal resistor less than resistance. Yeah, then resistor then lamp. Yeah, so in simple way, like R is small than R. Yeah, so the energy the potential difference across the lamp must be less than the EMF of the battery. Yeah, that's it. Question I calculate the current in the circuit. Okay, current I think we don't use about Ohm's law, but we use about I as a charge over time. Yeah, because we already have 750 column of charge here, and on the time 1500. So this is a half. Yeah, a half ampere. That's it. Okay, the potential difference across the lamp. Potential difference across the lamp. PD. Yeah, PD on the lamp is IR. Oh, wait. I think we don't use this formula because we already have about W. Yeah, we can VIT or V, yeah, is same thing with W over key. Yeah, W we have 5.7 kilojoule. Kilo means 1000, yeah, or times 10 to the power 3. And Q we have 7.5. So potential difference is, wait, 5.7 divided, okay, this is about 7.6 volt. Okay, this is potential difference across the lamp. Yeah, and then finally we need find about internal resistance. Here is voltage is 7.8 minus 7.6 divided electric current. Yeah, so this 0.5 sorry 0.2 divided 0.5, 2 over 5, 0.4. Yeah, 0.4 ohms. Yeah. That's it, done. Then still have some question here. Yeah. Question B. Yeah. Student is provided with 3 resistor, 90 ohms, 45 ohm, and 20 ohms. Sketch a circuit diagram showing how two of these 3 resistors may be connected together to give combined resistance 30 ohms, yeah, between the terminals. So label the value of resistance on your diagram. 30 okay, wait, connected together. Sketch this diagram how two of these 3 resistors. I think about 90 and 45. Yeah, we check. Let's say 90 and 45. Yeah, this is 1 over R equivalent when on the parallel. 190 plus 145. Yeah, so this is like 1 plus 290. Yes, this is about 3 over 90, or R equivalent is 90 divided 3, yeah, about 30 ohms. So from this, so this is about parallel, yeah. Yeah, we can draw it as like this one. Yeah, parallel between 90 ohms. Yeah, this is 90 ohms. Oh my god, sorry, it's about 90 ohms and 45 ohms. Sorry, yeah, Okay, done. Yeah, that's it. Because after I calculate, yeah, combination between 90 and 40, yeah, become 30, yeah, 30 ohms. Okay, still one more question. A potential divider circuit is produced by connecting the three resistor of to the to to a battery of EMF 99.0 volt and negligible internal resistance. The potential divider circuit provides an output potential different V output of 3.6 volt. The circuit diagram shows in figure 6.2. Okay. Oh, I see. So maybe these are, yeah, here is 90 ohms and here is 45 ohm, and one more is 20 ohm, yeah, 20 ohm. So when, yeah, when we find V out on this point, yeah, this is same thing with 20 divided total resistance. Total resistance same thing with 30 plus 20, yeah, this is 50 times 9, so equals to 2/5 kali 90. This is equal 3.6 volt. And when on this position, this is something with 30 divided 50 total resistance times 9.0, 3/5 times 9 equals to, this is 5.4 volt, yeah, here. So you may see this here between 3.6 and 5.4 when we add. This is something with 9.0 volt, yeah. So we can like prove it, yeah. Okay, that's it. Okay, done for question 6. One more question, question 7. A nucleus of an element X decay by emitting a beta positive particle to produce a nucleus of potassium 39 and neutrino. The decay represented by, state the number represented by each following letters. Start from beta, yeah. Beta is the electron, yeah. Beta is electron. And electron is 0 minus 1, yeah. So we can decide P is 0 and R is minus 1, yeah, from this, yeah. So P0 39, Q is 39. Oh no. And S is equals to 18, yeah, because 19 minus 1, yeah, 18. That's it. Yeah. Then state the name of interaction force that give rise to B positive decay. This is from 1 x, yeah, becomes 2, so this is like fission, yeah. Fission, oh, sorry, fission. That's it. Okay, I think enough for this explanation. So thank you, you already watching this video until the end. So we can see on the next video. Yeah, okay, thank you everyone, don't forget to subscribe. Yeah, thank you everyone, thank you.